Everyone, my name is indeed Ruben Mechelinck. I'm from DistriNet Leuven, and I will present our BROL paper, BROL cache-only execution for software protection. So, software protection first is the field where we try to protect software against things like piracy, reverse engineering, unauthorized deployments, etc. So this goal is a little bit different than most other security-related talks here today. Anyway, so in particular, it's about protecting industrial software. So that's software that runs on these kinds of machines, right? And this software, is or contains intellectual property that or that is a target of bad actors. Bad actors like end users who want to use the software illegally without buying it on their machines, or maybe more harmful, malicious competitors that try to reverse engineer the secret sauce of the software, or try to resell it on hardware clones, for instance. The thing with these machines in your typical industrial setting, there are like PCs for heavy calculations, central controllers for controlling assembly lines, and microcontrollers in edge devices. And the thing with these devices is that there's, some of them can be very old, for instance, 10 years old maybe, depending on the industry, maybe even older. Some don't have network connections, some run bare metal software, and many of those also don't have dedicated hardware features things like trusted computing components, TEEs, and such, that could otherwise have helped in protecting the software. And the lack of these hardware features makes it very easy for an attacker to extract the software, either software as a whole or bits or pieces of it. That can either be from the on-disk image or from the memory image. The most dangerous situation, I would call it, is when our attacker, the thief, has or buys a genuine machine for themselves. Then they have full control over the hardware, over the software. They can tamper or change the hardware or replace the software, like run a different kernel, for instance. So that's the kind of attacker that we try to defend against here with BROL. This feared person at the end attacker with full control over the hardware and the software. So BROL builds on two building blocks. One of them is how the instruction caches typically work. The other one is physical memory aliasing. So about these instruction caches, CPUs with caches, they typically have a separate data cache and instruction cache at the cache level closest to the core. And there is a cache coherence protocol that runs on the CPU, right, to track where data is and in which data it is across all these different cores. This cache coherence protocol only applies to the data caches and unified caches, and not to the instruction cache, because there's usually no need for it. The instruction cache is hooked up to the CPU front end, it's not connected to any like data path, for instance. The CPU cannot perform any data read, data write operations on content that's in the instruction cache. So this data is never in a modified state. For that reason, any flush or evict will just discard this information, this cache line. So without writing it back to memory like it would with a data cache line in a dirty state, for instance. Same goes for cache-to-cache transfers in a multi-core system. The cache controller or the Snoop control units will not use the cache lines in the instruction cache for this. So in a sense, everything that enters the instruction cache, well, never comes out again, at least not in a recoverable way. So we use this property here in BROL to use the instruction cache as some sort of safe storage, at least to protect against like pirates and reverse engineers. Our second building block is physical memory aliasing. So when you have your physical memory, you make a request to it or an access. What happens behind the scenes is that the memory controller will translate your physical memory address to a DRAM address, and the memory controller is specifically controlled for the current memory configuration, right? And it gets this information on systems with replaceable memory. At least it gets it from the SPD chip on the memory DIMMs itself. On systems with a fixed memory configuration, things like microcontroller boards or single board computers, there it's usually hard-coded in the bootloader, the first stage bootloader. So what this earlier work by Jesse de Meulemeester does is they tamper with this information, this memory configuration, effectively misconfiguring or misinitializing the memory controller. Such that it thinks that there's twice as much memory, right? Because we increased the row bits, so it thinks there's twice as much physical memory, and it in turn presents the operating system with a physical memory area that's also twice as large. However, if we access an address in this part, then the memory controller translates this address to a DRAM address. But this extra row bit is not connected to any physical address line, so it's dropped, right? And what will happen is that you will access like the same location in DRAM as the address in the upper half. So you will read the same data from there, and these addresses they alias. In this paper by the Meulemeester et al., they use this primitive to attack trusted execution environments. Later today, you will hear another paper that builds on this primitive. We use this as a primitive to create cache incoherences. So when you have this setup, right, you perform a load operation, you cache the data as such, and then you store something else through the aliasing address. And so it updates it there and on these locations as well, because they alias. And then you end up in this situation where you have stale data. The data in the cache is different than what's in memory. The CPU only saw a store instruction that is to a different physical address, so it's not aware of this incoherence, right? It will not run any coherence operation here. All right, so those are our two building blocks. Now, how BROL actually works to protect against software theft. We start with the binary stored on disk. We store it in an encrypted form, and we suggest using a memory puff to derive the decryption key, so a physically unclonable function that operates on memory. I'll explain the reasoning behind that later. Then when we start the program, we decrypt it, load it in memory as such. Then we run it a first time to load it in the cache by running it on some dummy data, for instance. So it gets loaded in the instruction cache. Note that I only show here a CPU with one cache level. I'll also talk more about that later. So this is what you can typically find in a microcontroller that has caches, things like your ARM Cortex M7, M35, M85, that sort of chips. Right, so once we are in this situation, we override the codes in memory through this aliasing area. We zero it, for instance. So now the code is not present anymore in physical memory. It can still run the part that it's loaded in the cache. But it's gone from memory. So how does this actually protect against pirates? Well, so the static image I stored on disk, as I said before, is encrypted. So yeah, it's not readable from there, at least if the attacker doesn't have the key. I talked about the puff. We use a puff to, in essence, bind the software to one particular hardware instance. An attacker can just not simply copy the software and deploy it on any other machine because it will have a different puff response. We use a memory puff in particular to bind that software instance to that particular aliasing-enabled memory configuration. If an attacker, for instance, would disable memory aliasing and replace the second half of the address space with real memory, then that half would give a different buff response, effectively deriving the wrong decryption key. So launching the program will also not work in that case. Everything that's stored in physical memory is cleared, so our powerful attacker with full software control cannot extract the software anymore from memory. Also, many kinds of dynamic analysis rely on a valid memory representation of this code. Things like debuggers, instrumentation tools, for instance, they need a memory version of this to run their analysis. Tools like processor tracers, Intel PT, for instance, they don't need the code in memory, but to get all the info available, you need to map the captured instruction pointers back to a valid memory representation, which is absent here. And then the cache image, like I said before, once something enters the instruction cache, it is hard to get it out. At least in this system with a single cache level. All right. About these multiple levels, and the issue there is that when you load the program like before, the code also ends up in the level 2, level 3 cache, these unified caches. Our powerful attacker can simply read the code from there, or transfer it to other cores or dump it back to memory, right? To thwart this, we came up with the genius idea to try to evict the protected code from the unified caches by flooding these caches with junk data while keeping the code present in the instruction cache. So this is on a system with non-inclusive or exclusive caches. The thing is that there there isn't much documentation on the inclusion policy, on the replacement policy, on this kinds of stuff, while BROL really needs certainty about whether the code is still present in unified caches or not. So there is a whole body of earlier work that tries to reverse engineer these properties, the directory structure and such. But we decided for now to not go into this rabbit hole and leave this as a nice problem for future work. Well, since I'm already 40 minutes in, I will skip this. I'm sure you will have questions about it, and go straight to the conclusion. So we designed BROL, a system to protect software against piracy, reverse engineering unauthorized deployments by binding it to a hardware instance and running it from the cache. Right now we are limited to systems with a single cache level, like microcontrollers. Okay, I think I can end here, and I'm ready for your questions.
Thanks for the talk. Any questions Okay, I will ask the first question. How about the instruction prefetchers? Would they have any effect of the code in the instruction cache?
Well, yeah, talking about these instruction prefetchers, we did have some issues with what we call unwanted evictions. That part of the preloaded code got evicted by, for instance, by prefetchers that might interfere, or other code running on different cores, for instance. So yeah, that is indeed an issue. We ran our evaluation on a number of programs to find out if which code sizes are really affected by these unwanted evictions. Yeah, and for real world programs, we found that this border is about at 1 kilobyte. So everything below ran smoothly without unwanted evictions, without interferences. Everything larger did encounter some issues with that.
Sorry, one very simple question from me. I imagine here. Just maybe it's outside of the threat model here, but just to understand that if I understood clearly. So if you were able to rehost, for example, the firmware image, or run it in an emulation environment, then this trick of aliasing the store, the addresses wouldn't be an issue anymore, right? Because the emulator, for example, would see different addresses, and then you would be able to see the actual decryption of the thing completely. Is that?
I didn't hear that quite well.
So I'm imagining, for what I understood, the basic trick that you're using here is this aliasing of DRAM, right?
Mm-hmm.
So one store in another physical address ends up overwriting another address, right?
Yeah. Correct.
So I was thinking, if you're emulating, for example, this firmware image, then at that point you wouldn't have this trick, right? So you wouldn't see something like that, right? So if you extract the image and you're able to emulate it, it wouldn't do this over, like you wouldn't be able to use this, right?
Yeah. So indeed, there are many kinds of attacks really that work. So yeah, the first thing to emulate the program, you would need to extract it and decrypt it. So that is one attack where you get the key from the machine itself and decrypt it, and then you won't even need to emulate it. You could just decrypt it, and you have the code for you, right?
Maybe a short question. If I understand you correctly, at the very beginning, when the software, so to speak, starts up, the instructions are, so to speak, unencrypted in DRAM until you fill them with zeros with your trick.
Mm-hmm.
How long is this time frame when they're, so to speak, theoretically still recoverable from DRAM?
How long is the time frame? Well, as long as it takes to load the program in the cache. So that's very short, I would guess. That's the main benefit also of BROL. You reduce the time window of the attack to only like the startup time instead of the whole duration of the program.
Thank you. Let's thank the speaker again.